Hello everyone, welcome back to Math with Allison. Today we're working in our Calculus 2 series and we are doing our first exam. Woo woo! Here we have a real college exam. This was given in the fall of 2015. It is currently given to students as a study guide to prepare for their upcoming exams. So let's go and go through this. We can see on the front that there are going to be 7 questions and we can see how many points each are going to be worth. So 4 and 5 look a little important. They're 20 points each, but you do you. So let's go ahead and go through this thing. We're going to start with question 1. We are going to write an integral representing the arc length of the graph y equals natural log of x on the interval 1 to 2. And we do not need to evaluate this. That is so nice. So basically, you are going to get 10 points by remembering the integral for arc length. So here we have L is equal to the integral from a to b of the square root of 1 plus f prime of x squared dx. If you want to see how that's derived, I have a whole video on it, and it has to do with the hypotenuse of lots of triangles. So you can go ahead and go through that if you want. Otherwise, you can just memorize it. And so here we have the interval is from 1 to 2, so that tells us what our a and b is going to be. And then we have the square root of 1 plus, and now we need to take our first derivative. So the derivative of natural log of x is just going to be 1 over x quantity squared dx. And you literally just get 10 points for remembering that. So that is super nice. Our next question is we want to find the area of the region bounded by the graphs y equals x cubed divided by 4 and y equals x. So here, let's go ahead and label these functions. We have y equals x is going to be that blue function. It is going to be the straight linear line. And then our other function is going to be our cubic function. So that's going to be in red, x cubed divided by 4. So notice here that we are doing this from the points -2 all the way to x equals 2. So we are actually not going to be able to set this up as one integral. Because remember, the area between two graphs is going to be the integral of a to b, and we take our upper function and we subtract off our lower function in terms of dx in this case. It could also be dy, in which we would do right minus left, so I'll write that down. So in our case, of course, we're going to be doing dx because we're going to find the distance between these two, which go corresponding with the x-axis or the x variable. So let's go ahead and talk about our upper minus lower. Notice that we're going to have to set up two different integrals because the upper switch. On the left side, we have our upper is the cubic function, and on the right side, we have our upper is the linear function. So let's go ahead and set up our two integrals. So first in the blue, we're going to have the integral between -2 of 0. We're going to take our upper function, which is x cubed divided by 4, and we're going to subtract off our lower function dx. So now we want to go ahead and find our other area, which is going to be this one right here, in which we're going to change our functions, upper and lower, and our bounds. So this is going to be between 0 and +2. Our upper function is now going to be x, and we subtract off x cubed divided by 4 dx. So now that we have these two different integrals, we can go ahead and evaluate it. So here, what we're going to do is take the antiderivative. So I add 1 to the exponent and divide by that new exponent. So that's going to be 4 times 4. And we get minus x squared divided by 2. And this is going to be between -2 and 0. Plus, and now we're going to get those same values but switch. So x squared divided by 2 minus x to the power 4 divided by 4 times 4. And that's going to be evaluated between 0 and 2. I'm going to go ahead and clean this up a little bit. Okay, so now what we're going to do is plug in upper minus lower. So I'm going to go ahead and do that. So here we can see everything that's going to go to 0. It's going to be this term and this whole term. That's all going to be 0. So let's go ahead and simplify these out. Do not forget we have to distribute this minus sign to both of them. So -2 to the 4th is going to be 16. So that becomes -16 divided by 16. And now that becomes +4 divided by 2. And now we're going to take this +4 divided by 2 minus 16 over 16. So here we can go ahead and simplify them, or you could have right away. -1 plus 2 minus 1. And so here that becomes a 1, and this also becomes a 1. So we get 1 plus 1 is equal to 2. And that right there is going to be our final solution. There is another way you could have looked at this, and you could have used symmetry. So we have that both of these little areas that I've already colored in are symmetric. They're exactly the same. So instead of setting up two different integrals, if we use symmetry, all we would need to do is take one of the integrals. So I'll take the 0 to 2, x minus x cubed divided by 4 dx. And we would just multiply that by 2 because we're getting two of those areas. So that is another way you could have done it. Both of them arrive at the same answer of a value of 2, but one of them maybe is a little less work. So for question 3, we have some circle your answers. and we're going to go ahead and go through it. So if a region R is in the first quadrant and is revolved around the x-axis, the disk or washer method requires, and we're going to figure out if it integrates with respect to y, integrates with respect to x, or cannot be applied. So I suggest, if you don't already have what it does memorized or understood, draw a picture. So I'm just going to go ahead and draw a little picture. We could do something like e to the x. E to the x, I'm going to choose a value right here, and we're going to go ahead and rotate this region. And we're rotating this, revolving it around the x-axis. So it would go ahead and appear like this on the other side, and you can pretend that those are totally symmetric. So now if we are going to go ahead and use disk or washer method, then our slice would look something like this. So I'm going to draw in that circle right there, and I can draw it right here to make it look a bit more nice. And we know our radius is going to extend from the x-axis all the way up to our function. And so our radius is going to be e to the x, right? And that's going to represent the radius of our circle. And we know the area is equal to pi r squared, so e to the x squared. And when we are integrating, we're integrating all of these different areas because we're adding up all of the tiny little slices. And so this means I'm going to be integrating with respect to the x-axis. So notice when we have disk or washer method, so when we use a method of slicing, whatever axis we're revolving around, we're also going to be integrating with respect to that same axis. So the same thing is going to be applied for when we're revolving around the y-axis with a method of slicing. We're going to go ahead and integrate in terms of y. And if you want to think about it, try drawing out a picture. So now let's go ahead and think about the shell method. Is it going to be the same? Is it going to be the same variable? So with shells, it's actually going to go ahead and be opposite. So when we're revolving around the x-axis, we're going to be integrating with respect to the y. And now when we're revolving around the y-axis, we're going to integrate with respect to x. And so that has to do with cylindrical shells. So if we have something that's revolved around the x-axis, we're going to take a length and we're going to revolve it around here, right? And so this is what our cylindrical shell would look like. Now, of course, what we're going to take into consideration is the h, the height, right? And you can think about it as which axis does it actually stab. So the height is going to go ahead and stab the y-axis. Now, if we were to revolve around the y-axis, so here if I drew out a cylinder, I'll take part of our function and we're going to go ahead and revolve that all the way around. So it looks something like this. Now, if we think about our height is going to be stabbing the x-axis, so we're going to integrate in respect to x. And actually, this works for the disk and the washer method. Here, the radius is stabbing the x-axis, so we integrate in terms of x. And if we were to draw a visual like this, we would have something with our radius revolving all the way around. We'd have a circle like that, and we would have that our radius is stabbing the y-axis. So I have videos on how we can do shell method, washer method, all those different things. You can check them out for a deeper explanation of why. So here we're going to move on to question 4. We want to use the method of slicing to find the volume of the solid of revolution formed by rotating the region bounded by y equals x squared divided by 4, so we can see that's the red function, in the horizontal line y equals 1 about the y-axis. So I already drew it out here. We're going to be rotating around the y-axis. So we would end up with a like bowl-looking thing that looks like that, right? So let's go ahead and talk about how we're going to go ahead and set this up. Method of slicing means we're literally going to slice this in half or something like that. And so what would one of the slices look like? Well, it would look like a little circle. So let's go ahead and draw out that circle. We know how to find the area of the circle. The area is equal to pi r squared. So here we can go ahead and find what our radius is equal to. So we extend from the y-axis all the way out to our function. And so this right here represents the length x. If I were to mark it right here, I would go a length of x. So here we have that y is equal to x squared divided by 4. So I want to go ahead and actually solve for x. Here we get 4y is equal to x squared. Take the square root of both sides, we get 2 times the square root of y is equal to x. So here we can plug this into our area. Area is equal to pi times the radius, 2 times the square root of y squared. And here that becomes 4 pi y. So now notice that we are going to be integrating in terms of y, and that also helps from that multiple choice question we just did. So here we're going to add up all of these areas, which is the integral. And so here we're taking slices starting from 0, and we're taking slices all the way going up to 1. So that tells us our bounds 0 to 1 of all of our circles, 4 pi y in terms of y. So let's go ahead and integrate this thing. 4 pi is just a scalar, so we can take it out. We don't need to worry about it. And now we're just integrating y. So here we get 4 pi times y squared divided by 2 between 0 and 1. So when I plug that in, I get 4 pi, and that becomes 1/2 minus 0. And 1/2 times 4 pi, that's just equal to 2 pi. And that right there represents our volume. So here, that moves on to question 5. We're going to use the method of cylindrical shells to find the volume of the solid of revolution. And we're going to do the exact same thing. We're going to rotate around the y-axis like this so it becomes a bowl again. But this time we're doing shells. So let's go ahead and talk about what a shells would mean. It would mean that we literally just took a cookie cutter and we literally slice it. So here we would have a cylinder that looks something like this, right? Now what we do is we take that cylinder and we unroll it. It's like we cut it and we lay it out flat. So this long length is equal to the circumference, which is 2 pi r, and this other length is equal to the height. So let's go ahead and find what these values are equal to. So I want to go ahead and find the radius. So the radius is going to extend from our axis all the way out here. And again, this is going to represent a value of x, right? This whole thing is equal to x. So our radius is going to be x, right? And so now let's go ahead and talk about our height, which is here highlighted in blue. So our height is going to be, we're going to take the full length of 1 and we're going to subtract off this length of y. So 1 minus y. And so here our height is going to be equal to 1 minus y, which we need to replace y. And we know what y is equal to. So we get 1 minus x squared divided by 4. So let's go ahead and fill these in. We got the area of this rectangle is equal to 2 pi times the radius, which is equal to x, multiplied by the height, which is 1 minus x squared divided by 4. So if you wanted, you could simplify that real quick. We can multiply that x in, and we get x minus x cubed divided by 4. So let's go ahead and set up our integral. We have volume is equal to the integral. And notice here, what we're going to be doing is we're going to be taking all the slices starting from 0, going all the way out to 2. So we have the integral from 0 to 2 of 2 pi x minus x cubed divided by 4 dx. So here that 2 pi is a scalar multiple, so it just hangs out. We get x squared divided by 2 minus x to the power of 4, and we get 4 times 4, which is equal to 16, between 0 and 2. Here we can plug in upper minus lower. And when I plug in 0, that whole thing goes to 0. So now we can go ahead and simplify it. I'm going to bring it over here. So we get 2 pi, and we get 4 divided by 2, which is 2 minus 16 divided by 16, which is 1. So it becomes a value of 1. 2 pi times 1 is just equal to 2 pi. And notice here we get the exact same solution. And that's because no matter which method you use, you're going to end up with the same volume, right? Okay, here we go with question 6. We're going to go ahead and take the derivative of the natural log of cosine of x. So when we take the derivative of natural log, we put whatever is inside the natural log on the bottom, so cosine of x, and in the numerator, we put its derivative, so negative sine of x. If you wanted to simplify it, you totally could. That becomes negative tangent of x. Now we have the definite integral of that whole thing, and notice we have sine of x divided by 2 minus cosine of x. What I notice here is I see something along with its derivative. So I want to set u equal to the denominator because I see its derivative in the numerator. So I get du is equal to, that becomes 0 minus negative sine of x dx. And here you could simplify that out. That becomes du is equal to positive sine of x dx. Which that is going to be super nice because I can directly plug that in right here. But don't forget, this is a definite integral, so we also need to change the bounds. We have what x is equal to, and we want to solve for u. So our lower bound is 0, and our upper bound is pi over 2. Here we can plug that into 2 minus cosine of 0. Cosine of 0 is equal to 1, so we get 2 minus 1, which is equal to 1. So here we have a new lower bound of 1. And we also have 2 minus cosine of pi over 2. Cosine of pi over 2 is equal to 0, and so we get a new upper bound of 2. So here I can plug all that in. I get 1 to 2, 1 over u du. And that's super nice. I get the natural log of u evaluated between 1 and 2. So here I can plug in upper minus lower, and we can take this one step further because the natural log of 1 is just 0. And so this right here is our solution. We got one more, part C. We have the integral of e to the 2 root x divided by root x. So if you don't get your u substitution correct the first time, that is totally fine. You can try a couple different times. In this case, I know the derivative of the square root of x is 1 over 2 square root of x. And I already noticed have a root x in the denominator. So what I'm going to go ahead and do is I'm going to go ahead and set u equal to the exponent, 2 root x, or you can write that as x to the 1/2. So when I take the derivative, I get 2 times 1/2 x to the negative 1/2 dx. And that simplifies nicely to du is equal to 1 over the square root of x dx. And notice we can see that directly in our integral. We get 1 over the square root of x dx. So let's go ahead and plug that in. We don't have any bounds that we need to redo, which is nice. And we get e to the u du. Now the antiderivative of e to the u is e to the u plus c, in which we can plug u back in to root x plus c. And there we get our solution. At any point that you want to check your solution to indefinite integrals, you can just take the derivative and make sure you get back the integrand or what's inside the integral. Question 7, we're going to evaluate the following derivative and indefinite integral, hyperbolic functions. So here we want to take the derivative of hyperbolic sine of pi x. So let's go ahead and use chain rule. We're going to do the derivative of the outside, so we get cosh of pi x. And now we need to multiply by the derivative of the inside, which is just going to be pi. Or if you wanted to write it, you could write it as pi times cosh of pi x. And that right there is our solution. So let's go to part B. Here we have hyperbolic sine times hyperbolic cosine, both of 2x dx. So in this case, I'm going to go ahead and use substitution. I'm going to choose to set u equal to hyperbolic sine of x, and you could also set it equal to hyperbolic cosine. You can do either of them, and you will end up with a correct solution. So here I get du is equal to, and we're going to take the derivative of the outside at the inside times the derivative of the inside. So if you wanted, you could rewrite that as 2 times cosh of 2x dx. So notice in our integral, we're missing that value of 2. So I'm going to rewrite it as 1/2 times 2 hyperbolic sine of 2x times hyperbolic cosine of 2x. So what I did was I just multiplied it by a 1. 2 times 1/2 is equal to 1. But now I have everything I need to use u substitution. I have 2 times hyperbolic cosine of 2x dx. So let's go ahead and plug it in. I get 1/2. All of that highlighted in purple becomes my du. And I have that hyperbolic sine of 2x. That's exactly what our u is equal to. So here I can go ahead and take the antiderivative. I get u squared divided by 2 plus some constant c. And we can go ahead and multiply those together. U squared divided by 4 plus c. And we can plug in our hyperbolic sine of 2x into u divided by 4 plus c. And that right there is our final solution. So if you felt uneasy about any part of these exams, I have videos on all of these topics which go into greater detail about them. But otherwise, if you enjoyed this video, I have many more like them, so make sure to check them out. They're linked down below. Otherwise, please give this video a thumbs up and comment other problems or topics you'd like to see done. Thanks for watching.